Good morning. So today I prepared to talk about targeted adversarial attacks on NeRFs. This work was in joint cooperation with Pázmány University, with Horváth András, and it was presented last year at the ECCV conference. So let's see what is the agenda outline for today. I will give a brief introduction about NeRFs, then I will speak about the generalizable form of NeRFs, and finally I would like to show how can we apply adversarial attacks on these NeRF networks. Okay, so what are the neural radiance fields? So NeRFs appeared a couple of years ago, and it was a major breakthrough in novel view rendering. So what are the inputs and what do we want to achieve? We have a sequence of images and we know the pose of each image. It means that we know the transformation from a world coordinate system to the camera, as you can see here. And after we have this set of images, we train a network, and then we are able to render new views from totally new poses that were not seen before. So how we can achieve that? So let's say that we have the first image and we select a pixel, then we can cast a ray between the origin of the coordinate system and the selected pixel. And we start sampling this ray. So we have a bunch of samples. And then we fed each sample, so the 3D coordinates and the direction, the viewing direction, to a neural network, which is a very simple network. It's an MLP practically. And the output of this network is the RGB color and the volumetric density of each sample. The volumetric density is telling us whether that ray can pass through at that point or it's hitting a surface. So we expect to have high volumetric density close to surfaces, and we have low volumetric density when there is nothing, so when we have empty space. So as you can see here, we have this ray, we have the samples, and the samples have their color and they have this volumetric density, and it can be represented like this. So when we have all this information, we can apply volume rendering in order to get a final color, which is this one. But in the beginning, we selected one pixel, so we know what is the ground truth color. So we can adapt the weights of this network, of this MLP, to achieve the ground truth color. And this is how we train an implicit representation of the scene, and this is how we can query this network for new pixels in new poses. Okay, here I have two videos. I will try to switch because they are not working from. Okay. So. Here you can see one of our meeting rooms in NOKIA. We practically had a couple of images. We trained on NeRFs, and then we had a new route. We created a new video with new renderings, which is also important to know that we can also create depth maps from the same scene. So this is how we can do practically 3D reconstruction based on neural networks, and we achieve quite good results compared to, let's say, SLAM-based approaches where we cannot do this kind of beautiful rendering. Okay, now I will try to go back, hopefully. Okay, so the next point is generalizable NeRFs. Why do we need these? As you have seen that in the previous example, we had a set of images for a particular scene, and the network was able to reconstruct that scene particularly. So in case if you want to model another scene, a new one, then we need to retrain that model in order to be able to create new views. And in case of generalizable NeRFs, the task is whether we can solve this kind of rendering problem without the implicit model that we created. So we want to do it in a general way. So if we have a new scene and we have new images, we want to create new renderings based on these images, and we don't want to retrain the network at all. So this is the, one prominent example of these generalizable NeRFs was the iBarnet, which was introduced 2 years ago, mostly. And here I would like to speak a little bit about the components. So you can see that we have the source views, and now these are inputs to this model. And then we say, and it's also important to know that we know the pose information between these, we know the relative pose of these images. So then we say that we want to create a new image in another pose which is close to the source views. Okay, so we want to find the pixel color at this point. We cast a ray, we sample the ray, but at this point we know the 3D coordinates of these samples. And since we know the relative pose between the images, we can project these 3D points to the source views. So now, for example, for this point, we are going to use information coming from source view A and B at these pixels in order to create the new color at this view. So in this case, the input of the MLP is a little bit different. So we have the image color, we have the viewing direction, and this is an important part. We have an encoding and decoder network which is applied to these source views. So practically we have some features that are fed into this MLP. Typically a unit is used for that, but you can use whatever you want. And after that, this MLP will give us two things. Will give us the color and will give us the density feature. It will not give us the volumetric density. And the reason is that the following. So in case of the NeRFs, we had the structure implicitly represented in the network. But in this case, the network does not have any kind of information about the structure of the environment. So it somehow has to figure out, based on the samples, where is the surface, or what is the actual depth of the rendered pixel. So in the first stage, we are creating a density feature vector, and after that, all these density feature vectors from the sampled points are fed into a transformer architecture. The information is shared between them, and after that, the volumetric density will be the output of this transformer. So instead of having an implicit structure, we share the information of these density features, and then we predict the volumetric density. And the last part, the rendering and the rendering loss, is very, very similar to what we had before. Okay, and now I would like to show you the details of this MLP, because several questions arise here. So how can this architecture work if we have different numbers of source views? We know that rigid architectures are not allowing that. So let's say in case if we have n images, we have these n features, and when we try to aggregate a different number of input sources, we are using the trick that was introduced in PointNet for point clouds. So we try to attach some global information to every feature vector, which is the mean and the variance of these feature vectors. And then we fed this in one by one to this MLP. So it's important that we do this one by one because we have an MLP here. And the output is a modified feature vector and a weight. This weight is important because we want to handle somehow the occlusions. So in case if the projection for a certain source view is occluded, then it's not useful for us, and we want the network to learn that. So let's say we have two good features which are not occluded. We do a weighted pooling. which means we combine these feature vectors based on these weights. We fed it into another MLP, and we have the final feature density vector, which is going to go into the ray transformer. Okay, so this is the part which is calculating the volumetric density, and the other part here we do a concatenation of the relative viewing direction. This is important because we say that in case if the relative viewing direction is closer to one image, then the probability to have the same color as that image is high. If we have a relative viewing direction which is further, then most probably the color will not be so good coming from that image. So we have another MLP which is going to calculate these blending weights, and finally we multiply that with the colors coming from the images, and this is how we get the final color. Okay, so here you can see an architecture that is capable of creating new views based on based on source views. So this can work well for general scenes. Okay, so now we have seen how the NeRFs work, how the generalizable NeRFs work. Let me give you a very brief introduction about adversarial attacks. So in case of adversarial attacks, we want to fool the network. So for example, in this case, we have this very typical panda image, and we fed it to a network, and the output is panda with this confidence. Okay, so it's cool. So now the question is, how can I fool the network? How can I change the input in such a way that for the human eye, you cannot distinguish the difference between the input image, but I want to have a totally different output. And you can do that. So let's say that you have a loss function which is represented here as J, and let's say I want to increase the loss by adding a noise. So I compute the gradients with respect to the input. And finally, I take only the sign of these gradients and I multiply it with a number which is a small number. And I do it for a couple of iterations. And finally, I will get this image as input, and the output of the classifier will be totally changed. So I will get a gibbon with a very high confidence. This is how we can fool the network. It shows how well these attacks work, and we can use this kind of attacks in order to improve the robustness of the networks by training the network with these kind of examples. Okay. So this was the fast gradient sign attack, and there is another one which is very similar but a little bit different. So instead of sending noise to the whole picture, we define a patch, for example. So in this case, we want to fool the object detector, and the way how we do is that we define a patch with some random colors, and we apply this patch to the image. And then we can have two different trainings. We have the untargeted training and we have the targeted training. In case of the untargeted training, we want to maximize the loss function with respect to the true category and the true bounding box. And then we are modifying the patch in order to achieve that. In case of targeted training, we say that, okay, here is this patch. we want to modify that just to have a new category that I define and a new bounding box, which is typically this patch. So here on the right, what you can see is that the detector was working fine if we didn't put any other information on the image. But as soon as we apply this trained patch on the top left, the bicycle was not found by the network. In this case, in the case of targeted attacks, you can see that we apply this patch on the top left. The network found it, so there you can see this red rectangle, and the category of the image is totally different, so it's not able to detect the objects. So this is how we can fool the networks. Okay, so now how we can fool the generalizable NeRFs. The trick was the following. So we had a couple of source views, and we rendered a new view for a specific pose. And then we said that, okay, so this is the rendered image. Let's say that I want to add some hallucinated object, this little red teddy bear, which is which looks very good. So we put this hallucinated object here, and then we said that, okay, the loss function is between the rendered image and between this modified image. And then, since every element of this network is differentiable, we were able to send back this signal back to the source views, and we modified the source views with very little, to have very little noise. So practically the difference was indistinguishable. And we were able to fool the network. So on the first column, you will see that this is the original rendering coming from 10 source views. Here we hallucinated the red teddy bear in this point, some artifacts here between the flowers. Here we decided to make this, well, I don't know, what is this, a little bit longer. And then we applied this adversarial attack, and we checked what happens to the new renderings. And the new renderings show that, okay, the red teddy bear appeared here, the artifacts appeared. Okay, it's not as good as here, but anyway, it's quite good. And the elongated bench also appeared. We measured the performance, and we have seen that in case if we have 10 source views and we apply this noise only to 2 views, then the PSNR is not so good. But if we start spreading the noise to each and every source view, the PSNR increases and the to loss decreases. And we managed to show that this technique works for the 2 different attacks, the low intensity attacks and the patch-based attacks. Okay, I think I run out of time, so thank you very much for the attention. And if you have questions, then please let me know. Yeah, I will be here. Okay, thank you.